right where we left off yesterday. And the next thing we were going to talk about is what a gradient field is. The good news is you already know what a gradient field is. We just haven't talked about it in terms of being a vector field and how you can sketch it and do all that stuff. So we'll just revisit it real quick. Recall that if we're going to use a different letter, phi is of the form phi of x, y, and z, then the gradient we do gradient of phi, and the gradient function was calculated by doing what? Partial derivatives of the function with respect to x, and that would have been the I component. Partial derivative with respect to y, that's the j component. Partial derivative with respect to z, that's the k component. Yeah?
Is phi an angle or just the
It's a
same
function.
function?
It's just a
So
function now. Yes. Yes. It's not an angle. Here. So this is a gradient field of the function phi. And at each point, the vector points in what direction? Direction of what? Increasing, yes. There we go. There we go. Max increase. That was one of the properties of the gradient, right?
Are we going to have to draw 3D vector fields?
Yes, all the time. No. You guys believe me? Oh, okay. Let's just draw a quick one. Sketch the gradient field of, we'll just go 2 variables. Phi of xy equals x squared plus y squared. Okay, so the gradient field is just the gradient of phi, which would be what? 2x, 2y. And if we sketch, obviously at 0, 0, there is no vector. If I go out to, let's say, 1, let me do this in purple. Now we have a vector with how big for the component? 2. And if we go up to 0, 1, now it's pointing up, because the vector would be 0, 2. If we go over to -1 on the x-axis, now it's -2, 0 for the vector. And 0, -2 would be the vector at 0, -1. In fact, if you connect these points, this was a level curve where phi equaled what? 1. And all the gradient vectors are normal to the level curve. Remember how we talked about that, right? They're pointing in the direction of max or steepest increase. We can draw more. Now that you kind of know what this is going to look like, I mean, so basically on the unit circle 1, you're always going to have a vector that's 2 units long, orthogonal to the level curve. And if we did one more curve, I guess, let's see.
Well, are you still drawing the gradient field, or what are you doing?
This is the gradient field in purple.
Everything?
The gradient field is in purple. The blue circle is just a level curve. I'm just connecting that back to what we did in chapter 13. Okay? And if we did one more level curve, a convenient one, like phi equals, if I go 4, I've already kind of over, let's do 9. Then that corresponds to a circle of radius 3. 1, 2. And now how big are the vectors going to be that are pointing away from the origin?
6.
18.
Remember, this is 3, 0. So it's going to be 6, 0. And no matter where we are on this level curve, they're all going to be the same. They're all going to be the same length. So these get larger and larger. Now we just drew all over the notes. Oh boy. You get the idea. Oh. There we go. So you can pretty much picture, if you just randomly started at a point, what you're going to do. Okay? This is what the gradient field is showing us. That's the connection to what we did in chapter 13. Okay? Now, let's go on to the next definition. We say that a vector field F in any dimension, 2 or 3, is conservative in a region if it is the gradient actually, let's say the gradient field for some function.
Wait, so is it gradient field for some function or
Oh, the gradient field, either one. It's either one, of or for. You pick your favorite. For some function phi in that region. So here's what this means. We say that this is conservative as long as it's the gradient of some function phi. Okay, so that's what the definition of conservative is. Okay? This phi has a name. It's called the potential function. So right now, if we have a vector field and we're asked to determine whether or not it's conservative, you can say that it is if you can somehow find a potential function for which the vector field is the gradient of that, if that makes sense.
Like any gradient type function for it.
Not necessarily.
What's one we can't find function for?
We'll talk more about those in a little bit. Okay, but there's going to be, like right now, they're going to be pretty tame, so you'll know if we can find a potential function for it or not. Once they get a little bit more involved, we're actually going to have a specific test that we can check to see whether or not the vector field is conservative or not.
So right now we don't have to worry about it too much?
Oh,
No.
the vector field, not just one single vector.
Right, it's the whole field.
Okay.
Okay, so for example,
Wait, what was that? As long as arrow.
as long as this is true. So as long as this vector field
Plus you.
is the gradient of a function, okay, then we say that it's conservative. So for instance, here's one that we can look at. And for instance, I mean, this one I can tell you it'll be conservative. One that wouldn't be, if I had something like x squared comma x squared, that's not going to be a conservative vector field. Okay. Now this one, that's the question. Is this conservative or not? And I'll tell you right now that it is. And the reason is, if phi of x comma y, can you guys think of a function where the partial derivative of the function would be 2x and the partial derivative of the function would be y? Okay? Makes sense? So because this vector field happens to be the gradient of this function, we say yes. And the reason again is because the vector field is the gradient of phi.
So
J-Ram.
If they're like two different like variables, can you just take the integral of each one and just kind of add them together?
Yes and no.
okay.
That's actually going to be one of the methods we're going to use to figure out if it's conservative and what the potential function is going to be when it gets more involved. But it's not just as simple as just integrating and then done. There's something else you have to do after that.
So if there was a problem asking if a vector field was conservative, would you give us like that, and then we just have to say if it's conservative?
Right now, the problems I'm assuming in 11 or 15.1, which I haven't seen in a while, but they're either going to say show that this field is conservative by showing that it's the gradient of blah blah. So they'll give you a function, or they'll give you something like this where you'll be expected to find it. Does that make sense? And it should be doable. This is not the best way of finding the potential function. I'm telling you that right now. We're going to have a much smoother method of doing so later on. Okay? Okay. Let's move on. I think we can skip that proof, maybe.
Yes.
Maybe we should do the proof. No,
No.
just kidding. Let's just get to the last two things.
Yeah, that's actually for example.
Divergence and curl are the main things left, and then there's a little tidbit on the Laplacian.
Yes, no, actually, that's me.
Okay, here's what you need to know about divergence. Divergence relates to the way in which fluid flows away or towards a point. All these have to deal with fluid flow. Curl, it kind of sounds like it, relates to the rotational properties of fluid at a point. Okay, and again, we're going to do more with this later. Right now, you just need to know divergence and curl both deal with fluid flow. Divergence tells you or paints a picture as to whether things are flowing away or towards a point, and curl will tell you if there's any rotation going on at that point. Okay, so for instance, remember the hurricane vector field that we talked about yesterday? If you're standing out somewhere not in the eye of the storm, there's going to be some curl there because there's rotational properties in the vector field. Does that make sense?
Divergence?
There would be some, yes.
But then why?
Because you'd be at a point you're going to be going away. The fluid would be flowing away from the point.
If
It's
I'm-
going to also rotate, but
if
the only
I'm-
time there's no divergence is if you're like camped and you're not. There's no fluid movement at that point.
So even if something is like just circling around, you're keeping a constant like radius away from you, it would still have divergence.
Mm-hmm. For example, we could have a vector field that's all straight. Like remember the first example we did where we had, I think everything was pointing to the right on the right side, and everything was pointing to the left on the left side, right? There would be zero divergence on the x-axis, because if you're at that point, you're not going anywhere, right? But if you go anywhere outside of that, there is some divergence, okay? Because the fluid would move either away or towards a particular point, anywhere else besides the y-axis. Now, as far as curl, is there any rotation to that?
No.
So there's going to be zero curl for that. Does that kind of make sense? Now, here's how we calculate it. These are the definitions. So if we have a vector field in terms of x, y, and z, bless you, we're going to have three components. We'll call them little f without a little vector symbol to avoid confusion, little g, and little h. The divergence, which is not capital D, sorry, is abbreviated div, and then we just do f. And the calculation is actually a pretty simple one. You do partial f, partial x, and you sum the partial derivatives. Partial g, partial y, partial h, partial z. This is the definition for the divergence of a vector field. All you have to know is that this is how it's calculated for now. Curl is another vector, not a value. Notice the divergence is going to give you a scalar. Does that make sense? Curl is going to actually give you some vector, and that's partial h, partial y, minus partial g, partial z. That's for the x component, or the I component. Partial f, partial z, minus partial h, partial x. That's the j component. And then partial g, partial x, minus partial f, partial y.
But also the cross product or something.
Yes. Usually all these look like cross products in the end, right? So you're not going to have to memorize this. That's kind of weird looking, right? Here's the easy way to do it. Alternate formula. We can say that the curl of f is going to be the cross product, or the determinant. Did you say cross product?
Yeah.
I thought you said determinant. It's not a cross product.
Sorry, I said determinant.
I was just so excited. I was like, yes.
So what's the difference? What's the difference?
Cross product.
It's- yeah. The cross product is calculated by doing a determinant. But right now it's just a determinant. Now, interestingly enough, when we define the del operator, Roma, you could write this as a cross product. So you're right. We haven't gotten there yet, though.
I did say cross product.
You said both, right?
I said both. I did both.
Here's a shortcut, or an easier way to remember it. IJK. Second row is just the operators partial x, partial y, partial z. And then in the bottom row, it's just FGH. So if you kind of look up here, you can see that the I component would be partial h, partial y, minus partial g, partial z, and everything checks out. Okay, so this is a nicer way to remember it. All right, why don't you guys try this example? Find the divergence and curl for the vector field f of x, y, z equals 2x, y, I plus x squared plus z squared, j, plus 2yz, k.
Is FGH, are those the partials of x, partial y, partial z?
FGH are the scalar functions in here. So like this would be little f, this would be little g, and this would be little h. So today we're missing Nicole. There's no one that sits there, right? And then Charlie's there, but he's over there. Just Nicole. Okay. All right. Let's see. Volunteer Divergence. 4y. Tyler, how'd you get that?
Because partial f partial x is 2y, partial g partial y is 0, and partial h partial z is 2y.
Good. Pretty easy, right? Curl. Anybody have that?
0 vector.
Which means
There's no
there's no rotation going on there. Okay. Any question? Everybody get 0 and we're good? Yes. Eddie.
So then the divergence will change at each vector depending on what that.
Depending on where it is.
And then
Yes.
for the curl, no matter where it is, this is.
Yes. I mean, imagine a river. Depending on where you are in the stream, sometimes it might be flowing a little quicker, sometimes it might be flowing a little faster, so that could determine the size of the vectors if you think of terms of velocity. Does that make sense? But if you're just kind of flowing downstream, unless there's like some sinks in there where, you know, you get those little, you know what I'm talking about? Sometimes you get those little whirlpools in there.
That is, yeah.
Unless you have that in there, then it's all good. Yes?
What were the terms of that?
For the determinant?
Yeah, the curl.
You should have, let's see.
2z minus 2z.
So we have I, J, K, and then we do partial x, partial y, partial z, and then little f is 2xy, little g is x squared plus y squared, and then little h is 2yz. Oh. Thank you. So then, the first component would be partial y of this, which gives us 2z minus, and now we do partial z of this product, so that's also 2z. And now the j component, we're going to do the opposite of partial x of this function, which is 0, and then subtract partial z of that function, which is 0, and then partial x of the middle function is 2x, subtract partial y of this function, so that's also 2x. Okay, last thing. The del operator. We've used it. We used it as far as determining a gradient. That was a symbol we said determined for you. I need to find the gradient vectors for this function. On its own, just like that, it's really not anything. It's an operator. Just like a square root is an operator. Just like the log of something is an operator. It doesn't mean anything unless there's something inside it. Does that make sense? But if we think of it as this, and break it up into a vector with 3 little operators of its own, where the x component is the operator that means take the partial derivative with respect to x, and then y, and then z. Okay? Then we have a few different things we can do. The divergence of f, so if we go back, here, what could we do with this vector? And remember, typically we're going to have a vector field f with little f, little g, and little h, right? What can we do with this operator and this vector field to obtain this formula? Very good. So another way to remember the divergence of a vector field is that it's the del operator dotted with the vector field. Yes?
Why is that the same sign as the gradient?
Why is it the same sign? Because the gradient is a vector field. Like when we did this,
The gradient is the del.
does that make sense? This was the gradient of a function. This was the gradient. We usually did it like this, right?
Yes.
This meant the gradient of a function, which in turn becomes a vector field. By itself,
It's called the del.
it's just the del operator, which tells you to do partial x, partial y, and partial z, which is what this is. So we're just kind of breaking it down and thinking about it in terms of vectors. The curl, and you guys already saw it, would be written how? Cross product. So you pick your poison. If you want to remember the divergence and curl this way, as long as you know what this means, then you should be in good shape. If you are okay with the original definitions, this one and probably this one, I wouldn't recommend memorizing that, right? Then you should be in good shape.
It's right. I was about to say that too.
The Laplacian, and the reason I'm going to do this is because some of the homework questions will ask you to work with these operators and do some algebra. So we'll just kind of explore a little bit. This is just del squared. Which is the dot product of del with itself. So this is another operator. And the way you would take the dot product of del with itself is to just, take this and apply it again. Does that make sense? So what would it turn into?
Partial squared over partial x squared.
So what it means is to take the partial derivative with respect to x twice. That's all that ends up being.
Double derivative.
Mm-hmm.
Could you explain like real quick what an
It kind of did.
It's a symbol that does a certain
Yeah, an operator is something that tells you to do something to something else. Like, if you see a square root sign, you know what that means.
Tells me the square root.
Right. That's an operator. If you see something raised to a third power, you know what you're supposed to do with that. Does that make sense? Like, if you think of the calculator, if you look at your calculator, right? All those symbols, division, caret, square root, square, those are all operators. Because it's doing something to the input.
So it's like order of operation?
Kinda. Does that make sense, Eddie?
Yeah.
Okay.
And what does this do?
It's like I always tell my pre-calc students, sometimes I've seen this, especially if they don't know what they're doing. We're doing logs right now. That's an easy log equation that I hope all of you can solve.
Yeah. 25 x equals 24 equals x.
No, sorry.
Uh-oh.
Right? Is it wrong?
24.
I got 24.
X is 24. Okay. Now I've seen this one before.
Wait,
5 squared. So that's wow.
X plus 1 equals, and then they do some magic on the calculator. I have no idea what.
Whoa. How did
Because to you guys, you understand, log base 5 of what are you dividing by, right? And then they're like, well, what do you mean log base 5 of something? It's log 5. I'm like, no, it's base 5. It's an operator. And they're like, what do you mean operator? And then I show them this.
The Laplace thing?
No, I don't show them that. It'd be like if you were in trig,
Oh, the 6.
we obviously know where this scratch
Can you divide by sign?
and then you're like, oh, I'm gonna get excellent. I'll just divide by sign. And then they're like, well, we never did it that way. I'm like, of course, because it's an operation. Like you can't just divide by an operation. You can't just multiply
Divided by square.
by nothing. You know, like you need to multiply. You know what I mean? That's all an operator is, guys.
Divided by square root.
Anyway, let me finish what I needed to say.
If the sign of X
Divided by
is squared.
So now, if this is applied
6 of X.
to, let's say, a function, phi of x, y, z, then we say that del squared phi, in other words, the Laplacian of phi, would just be oh, you know what? Did I mean to do this? No. I think we're okay.
I think we can
Would just be to do this.
Wait, isn't that what we just said?
Well, if we apply it to a function, now you have something to take the partial derivative of
Oh, I see what you're saying.
x twice with respect to.
The sign of
Does that
something
right?
is-
Exactly.
Okay. Got it.
Which can also be written as, just so you guys see some of this algebra. Could I say that this is the divergence of something? Because isn't the divergence just the sum of the partials? But we have partial derivatives twice here, right? So this would be like the divergence of the gradient of phi. Does that make sense?
Oh, yeah.
Because the gradient of phi would give you another function, but it'd be partial phi partial x plus partial phi partial y. And then if you apply the divergence of that,
But could we make the divergence of the divergence or no? Is that...
well, we would need a dot product, right? Because the divergence is the dot product of del with the function, right? Okay.
So what does that mean? Like, what is that? You're just gonna.
It's just
Don't worry about it.
Nice to know.
You just
Nice to know.
you just need to know that
Was that the end of
that there's lots of different ways